Good morning. My name is Dan Ambre. This is the third installment of three different setups on webinar for Grace Engineered Products, Introduction to Vibration Analysis. And let me get to my starting point. And thank you for joining us. I see there's over 300 people that are already on the line. Thanks for coming back. This is the third installment. So if there's something that you see in this one, I might brush past it a little bit faster on one of my reviews. You can go back to that first seminar in last Tuesday and see a really good overview of everything. I just hate to be redundant on every succeeding webinar, or at least I feel I'm redundant, and I'd rather get into a little more information. But and also, if you please recognize that this is normally a 2-day class. So I'm taking 16 hours and turning it into 3. So there's a lot that you will miss. I mean, this is just a brief overview of everything, just to get you oriented to vibration. You might be able to answer a question or two from your vendors or your salespeople, but you obviously won't know everything about vibration. I've been doing this for 30 years and I still see things monthly that surprise me. But anyway, full spectrum diagnostics, we do training and certification, live training, AS&T and ISO based guidelines. We also have a lot of interactive stuff. So I've been doing these webinar short courses, and then I also have an online learning management system software that takes subscriptions for on your own learning, or learn on your own time, basically. And they're used as troubleshooting or as formal teaching. It doesn't either way. What you see on the screen is the vibration fault periodic table. We'll touch on the various aspects of it today. It is the backbone, it's the framework structure for learning vibration, I believe, but also doing analysis where you can walk through and slowly eliminate problems by frequency content, by directional response, and then zero in on the root cause. Okay. We also, we also have, why isn't this working? There we go, sorry. We also have a Machinery Analysis Division. We specialize in some high-end machinery animation analysis called Experimental Modal Analysis, which is frequency analysis for natural frequencies. We also have Operating Deflection Shape analysis of machinery. And the end product of it is something that can be usable and understandable by anybody. And the unit you're looking at right now, on this side, there's a steam turbine, there's a gearbox with couplings on both sides, and you're coupled up to a generator. And this was one of the actual problems that we solved. There are probably 300-400 measurements here, physical measurements we had to put down. But you can see right away, there's thrusting across this coupling. There's nothing on this side. This coupling is running beautifully. But we're thrusting this coupling and we're pitching the generator a little bit. So there's a couple of problems that we can see right away. And you might not know anything about vibration, but it makes total sense to see the motion. And this is a phase analysis, kind of phase on steroids, and we'll get a little bit more into phase analysis in this section today. The third little division we have is Emiscope ODS video. So instead of taking physical measurements, we take a high-speed video. The clip is processed. We enhance the displacements and rescale the amplitudes, and we can see what can't be seen visually. So there's something like 1.3 million pixels in each one of these images. Potentially we could use all those pixels. We only use about 10% right now to get an incredible view of what's actually going on. So today's analysis or instruction, Introduction to Vibration Analysis Part 3 is going to have a quick overview of the PDM process. We're going to have a look at the vibration fault periodic table and do an overview of that. So it's described as a logical sorting mechanism providing an analysis framework and methodology. And the whole idea is to eliminate faults until you get down to the root cause. We're going to look at basic vibration analysis that we started last time, and we ended up, had to cut it a little short. We were in the amplitude phase of it, and we're going to look at frequency and phase analysis today. And then the last section is ultrasonic vibration analysis and trending. This is how rolling element bearings fail. Up to now, we've been talking about basically trending the overall energy in the machine from the Grace transducers sitting on top of the machine, and we're not really picking up a frequency analysis. We're going to talk about frequency analysis. We can do that on demand if we wish. It's just a power consumption issue, so we don't do it all the time, but we're trending the overall level, okay? The ultrasonic vibration analysis is another measurement. It's a high frequency filtered measurement, and this is how rolling element bearings fail. If you have other problems like looseness, misalignment, bent shaft, cocked bearings, things like that, they'll fail at turning speed of the shaft. So they have a particular frequency group that you're dealing with. The ultrasonics, they'll fail at a frequency hundreds of times higher out in the ultrasonic range. So we're going to look at briefly at what that ultrasonic vibration is and how we can use it to trend the output of the Grace transducer. Okay, the overview, the very basics, we have the machine of interest. So we're going to choose a machine, and knowing the machine's important when you're setting up your database, because each machine has a different allowable vibration level based on it by design. Okay, they're not all the same. We're going to put our transducer on it. This is a calibrated transducer. You see something like 100 millivolts per G. That's typical. That will give us a value that means something. So the analog voltage output is voltage versus time. When we put this calibration factor in, we get acceleration versus time. So it's millivolts per G. So we get acceleration as our amplitude, time as our axis, and we have a usable signal. Well, not quite. The analog signal is infinite. Okay, it goes on and on. We can't process something like this. It would take us forever. Instead, we digitize it and sample it at a very high rate. So we can see all the dots here, and the dots are so close together they look like lines when you're done. So you basically turning this into a bunch of dots that are equally spaced so you don't lose any of the important information you're after. Okay, and so it mimics the signal and it sets it up for doing the FFT process. The FFT processor, fast Fourier transform, strips out all the individual periodic events out of the complicated signal. So we have this complicated time waveform with lots of wiggles in it. Each one of those wiggles corresponds to something. If you overlay them all, they're all the periodic events inside that trace. The FFT processor finds the subtle low frequency period. It finds the more dominant second period in here, and then there's a third higher frequency period involved. Okay. Not real important how it does it specifically, but that's the easy thing. So I can use a very simple mathematical equation. Frequency equals 1 divided by the period. If I know this period length, and it took half a second or something to do that, 1 divided by 0.5 is 2 hertz, or 2 cycles per second. Okay, so I have a frequency. I can do the same for all these. If I know how long this periodic event was, I can calculate the frequency it generates. So now I go from a time waveform or a time domain to a frequency domain. Okay, the only thing left out is how much is too much. F2 looks like it's the biggest peak, but we don't know exactly what F2 is. We go in here and we look at our machine, we get a strobe light out, we get a laser, we do something, we find out what the speed of the machine is. And we find out the speed is 1760. So F2 is my running speed, my turning speed of the shaft. F1 is something below running speed, and F3 is some frequency we haven't determined yet. If I know where 1 times RPM is, I can make my stair-step pattern. And this we talked about a little bit, I think, last Thursday. This stair-step pattern is giving me alarms on each frequency band. Okay, so I have a whole series of alarms now. And we'll get a little more into that. So we're answering the question, how much is too much? So if any one of these bands produces an amplitude that's above our limit, like this one or this one, we can go in and do some analysis and figure out what's causing that. And how we can deal with it. The vibration fault periodic table, it's a structure and method. It's a sorting mechanism. It has three different steps, basically. First is we're going to sort the vibration by frequency content. So there's synchronous, harmonic, sub-synchronous, non-synchronous, and modulation. These are all the columns on the tables. The second part of this, it's organized by directional response. These are the colors, the yellow, the red, and the orange. And after we're done sorting those two times, we organize our faults by a diagnostic. So we have 5 different diagnostics we can do just to sort out what's what. So in this case, if I think it's in a synchronous column, I have a bunch of phase diagnostics I would do, okay, to see which one of these faults is the culprit. If it's in over here in a non-synchronous range, I might use an ultrasonic or a transient or an oil orbit analysis to figure out the problem. Okay, so we're all working our way toward the root cause. The various components, synchronous is 1 times RPM or turning speed of the shaft, okay, rotating speed of the motor and pump and what have you. Okay, that's 1 times RPM. Everything in these 2 columns produces a 1 times RPM. They're very similar, okay. This is the only one little oddball. This is going to appear everywhere. The natural frequency is not it's a frequency based on mass and stiffness. So it's not based on some blades or gears or anything like that. It is all mass and stiffness. We have to disprove that it can occur anywhere. It's non-synchronous, but it can be close to running speed and still amplify. So we have to prove down the road here if this is a problem or if it's a phase problem in the third part of the analysis. So the first 2 columns are synchronous, turning speed of the shaft. There is a little bit of overlap, but the 3 columns, columns 2, 3, and 4 are harmonics. So they're exact multiples of running speed. And the easiest way to understand this is if I have 53 teeth on my gear, I'm going to get 53 times running speed, exactly 53. In every tooth that engages, I get a little bit of a pulse. So every revolution of the shaft, I get a pulse per tooth. So 53 teeth. If I have a pump with 5 blades, I'm going to get exactly 5 times running speed. And it's a pulsation in pumps and fans and compressors when a fluid is compressed past an obstruction. So in a pump, it's a cutwater. You'll squeeze that fluid, whatever it is, and it'll pulse as each blade goes by that cutwater. I guess might as well use the last one too. In electric motors, AC induction motors, you have rotor bars, and they're part of the design of the motor, but they switch back and forth from positive to negative polarity. So it's important to know if that sequence is working properly. You'll have an exact number of rotor bars. So it'll be 48 rotor bars, and you'll see a 48 times running speed pulsation. Okay, so synchronous, harmonic. My next grouping is sub-synchronous, and it's less than shaft turning speed, so below running speed of the shaft. Non-synchronous faults are basically anti-harmonic faults. They're not equal to multiples of shaft speed. They might be 5.12. They're not 5 times running speed. They're not 6 times running speed. They're actually a fraction, 5.125, let's say, times running speed. Okay, they're easy to recognize in the spectrum when you compare them to the turning speed of the shaft. The last is modulation type faults. It's a pulsing combination. So a beat frequency or something that generates sidebands in the spectrum. We have several examples of that coming up, so we'll cover that pretty well. Okay, so there is the vibration fault periodic table. We do a sort by frequency. We do a sort by or directional response. In this case, that's the colors, and I'll show you that right now. If you see a radial response in your machine, then that's the red blocks. Okay, that means that axial isn't a dominant direction. We can eliminate it. If you see axial is a dominant response, all the radial ones go away. Okay, if you see orange or if you have a radial or axial response, it'll be an orange fault on the block. And these are usually by design. So a good example of that is a gearbox in the gear design. If it's a spur gear, it's more radial. If it's herringbone, there'll be an axial component. So the overall vibration could be either one of those. Okay. And lastly, we have the diagnostics, the phase, time waveform, orbits, transients, and ultrasonics. And these are inside each box. So let's say I have a synchronous fault. It's radial directed, my dominant direction. I'm going to have these 4 blocks, and they all have a phase icon in there. So there's a phase test that I can do for each to prove or disprove each one of those. Okay, and that's how the diagnostic works. So 2 sorting mechanisms, frequency group and directional response, and then the icons themselves are telling us what to do next and how to narrow it down. Thinking like a vibration analyst, this is kind of how the process works, and it's evolving, okay? All this wireless transducers and cloud data and AI systems, there's going to be a little bit of time before it's perfect, but this is the kind of the stretch we're looking for. Okay, we're acquiring data, we're doing overall trends, we're doing time waveforms and spectrum at selected positions on the machine. Minimum, we want to have a Grace transducer, they're triaxials. We'll put one on motor outboard, motor inboard, pump inboard, pump outboard. Okay, basically at every bearing. You want an X, Y, and Z response. So what you'll get is 12 measurements. The top block here are the overall levels, and that's primarily what we're sensing. We're looking for overall levels, we're checking for changes, something to go in alarm, and once that happens, let's say there it is, we're the block here and we get into the alarm range, then we're on demand going to say, hey, we need to capture a time waveform, we need to capture a spectrum, we need to review that and see if there's any alarms in that spectrum. Okay. We can also pull in plant process parameters, pump curves, fan curves that might be something that we can pick out that's useful in there, where we're operating on the curve when something like this happens and we get a high vibration. So it might just be an operational problem. The best efficiency point is right there where you'd have minimum vibration. You stray away from that on a pump and you'll either cavitate or recirculate and the vibration levels will go up. So if we can integrate those plant processes, it's fantastic. This one is something that Grace is working on. This is phase analysis. So we can look on the same transducer from X, Y, and Z's to see what the dominant response and the phase response is. But the real power in that is having the transducers talk to themselves. So I have 4 different transducers. There's a way that we're working on to sync all the clocks so that they all capture data exactly simultaneously and we get a good phase measurement. If that turns out, we can animate something like that and get a rough animation, but something that's going to tell us how the machine's moving, and that's part of this process to help us figure the underlying faults. Determine potential faults, update the rule base. Here I show that there's an alignment issue, a looseness issue, and a blade passing issue. So those are things that might not be an alarm yet, but they're things we can trend. So instead of just trending overall vibration, we might be able to trend the phase response, which is how the machine's moving, when did it start, how bad is it getting, and so forth. So we have a degree of analysis there. Then we acquire data all over again. So if we do this process over and over, every hour, every minute, what have you, we'll get incredible trends that we can then use to our benefit and extend the life of the machines. Okay, from last Thursday, we did some looking into the real basics, the time, amplitude, frequency, and phase, and they're all interrelated in many ways. The time waveform signal is the basic signal that we get. It's the first thing coming out of the transducer. We can turn it into a spectrum, but most of the time we're extracting a peak value out of it and passing that value on. Okay, so we're going to get an amplitude out of it. We can trend velocity signal coming out, but we can also trend, we'll find out in a few minutes, the ultrasonic end of that as well. So the time we're going to look at in a second here. Amplitude is in different units, mils and inches per second, or Gs. The dominant response parameter that we want to look at is velocity in inches per second. Frequency, that's up to you how you like to look at your data. Usually people, it's either hertz or CPM, so cycles per minute or cycles per second. You can also normalize your data and look at it in orders if you wish. Amplitude is how much, it's a severity parameter. Frequency is how often, so it gives us a look at what the source of that response, that amplitude change is when we go into the frequency domain. And the last is phase, and phase tells us motion and direction. And there's 7 different phase rules that we can apply to understand how the machine's moving. And they're all independent of each other. So one of them might say a bent shaft, the other might say a cock bearing, okay? And very interesting technology, and it's visual, so everybody can understand once a phase analysis is done. So we'll get into that. Time waveform, the basic signal, first analysis parameter. Time waveform includes all amplitude and frequency and phase, sort of. We'll get there in a second. The overall amplitude's very trendable. So what we're seeing here is the output of a triaxial accelerometer. So we have horizontal, vertical, and axial simultaneously. The interesting feature as far as what we're concerned with right now is tracking the amplitude. So I have an amplitude in horizontal amplitude, vertical amplitude, axial amplitude. And I'll have 3 different trend lines that I can run statistics on. I can also calculate the frequency, okay? And we'll get to that in a second, but the frequency won't be a parameter that we're interested in until there's some amplitude excursion telling us that there's a problem. Then on demand or by default, we can calculate the frequency content of the signals coming out of this and get a little deeper in depth. Okay, but right now it's just the amplitudes trending give us a really good idea. And X, Y, and Z in the bearings is the best possible way to go. There is phase information, and like I mentioned, you can do this manually, or you can do it eventually if we can sync all the transducers. And the best idea of phase is looking across the coupling. So let's say I'm looking across the coupling. There's been an amplitude change. We go and look at the 2 different Grace transducers that are talking to each other, and we note that they're in phase with each other. Okay, their time waveforms lay on top of each other; they're not shifted. Right, that would say that the coupling's in phase, and it must be something else, or not misaligned. If we see something like this, we see a 180-degree phase shift. Our tabs are completely out of phase with each other, and if we look at the time waveform, the waveforms are 180 degrees out of phase, right? So that's saying, yes, we might have a coupling misalignment. The third one is what we'd see in an unbalanced condition, whether it's residual unbalance or it's a faulty unbalance. We're going to see a 90-degree phase shift between vertical and horizontal. Okay, that 90-degree phase shift is the transducer, or the heavy spot has to go 90 degrees further from horizontal to vertical to be crossing the transducer. So now we see this out of phase time shift. Those are the 3 important frequencies or the phase definitions that we're looking at. Either it's in phase, it's a 90-degree shift, or it's out of phase. That's going to allow us to distinguish about 8 different faults. Amplitude-wise, how much? We talked briefly about this last Thursday. I'm logging the amplitude, so I got one little leader here, and I'm waiting for it to go into alarm. Okay, what is this alarm level? It's based on the machine. So I have a center hung direct coupled fan or blower system. My alarm level is going to be 0.325 inches per second. So here we're using velocity. That's where my alarm line is. Okay, and we'll start trending. Once we know the machine, we know what rough estimate of what the alarm levels are going to be. Now these are much more meaningful. Now, this is just January through December. This would be a route-like measurement. Walk around routes, you take your data every month, you log it into the database, and you get something sparse like this. If you're using a wireless transducer, you can command it to do it once a day. You can take data once an hour, what have you. So let's say we're taking it once an hour, and in a month, that's a lot of data points. You can see two different trends here. You can see a flat response going through here, and then you see a jump. And then maybe another trend like this. So two different slopes, but you see a jump right here. This is from month to month. That could just be slight misplacement of the transducer before you take your data, or many other things. But if you're a transducer that's magnetically mounted to the machine and staying put all the time, you don't have any of that manipulation. This might be actually some type of fault that popped up that's very subtle that we'll be able to get when we start filling in these dots with more data. So even though we're not getting a lot of frequency information or any frequency information until we do a spectrum, the amplitude's got a lot of stories to tell. So we'll worry about that a little bit. We can take our data and set our alarms or whatever in displacement, in velocity, or in acceleration. The next couple examples are going to explain why we're going to use velocity. Velocity is a very flat severity parameter, and it goes across a really big frequency range. Okay. My paperclip example about displacement last time. This is a SN curve, which is a stress versus cycles failure curve that's used in metallurgy and mechanical engineering. Why is it of interest to us? Because we can have low cycle failures where we get large displacements but very low number of cycles, and we can have high cycle fatigue failures where they have extremely long lifetimes, and it all depends on the amplitude. If we're doing displacement amplitude, it's a function of frequency, and I can prove that with my paperclip example. I'll do 180 degrees of displacement, and I'll go back and forth until I fail that paperclip, and it's about 5.5 cycles. Okay, so I did it 6 times for each one of these. So 5.5 cycles is failure for a displacement of 180 degrees, so I plot that on my line. Okay, I don't know what the exact value is. I'd need a strain gauge, but do the same thing at 90 degree bend. It takes much higher cycles to fail. So over 3 times longer it lasts, but its allowable is a little lower, okay? 19.5 cycles. My amplitude of displacement was half of what I was over here. And the third example is I have a 45 degree bend, and I bend that back and forth 45 degrees, and I get about 70 cycles. This is telling me my displacement amplitude is a function of frequency, function of number of cycles, okay? So if I'm asked, is 5 mils an acceptable vibration level, an acceptable displacement level, I can't tell you what that answer is. I would have to know what frequency we're talking about, so I could actually calculate where that falls, that 5 mil falls with respect to this allowable curve, okay? Maybe a little better example is low frequency limitations of overshoot. When you turn on an electric motor, unless you have a soft start on it, it'll pulse pretty good. You'll get a good overshoot where you've gone beyond the limit that you want to go, the tolerance limits. It'll settle back down and it'll run nice. Most fossil plants have base load capability, and that's what they're designed for. Okay, base load meaning that you turn them on and you won't turn that thing off for 6 months to a year, okay, unless there's some type of problem that you have to fix. People design for that. So for a base load plant, you might say, well, we can plan on having one start and stop cycle every month. So for 20 years, that's 240 cycles. And I can plot that on my LCF curve. So I can say, there's my max. I don't want to run anywhere above that. Well, now these plants are starting to be used as peaker units. So natural gas plants are taking more of a base load capability. They're turning on and off fans in fossil plants to adjust for load. What does that do? We still have, every time we start or stop, we still have the same amplitude. We're not following that allowable curve anymore. So we'd have 4 times as many starts, so 960 starts. So instead of 20 years of life, we'll get 5 years of life. If we do that every day, we get a ridiculous amount of starts and stops. 7,300, that's about 7 to 8 months of operating. Okay, so that we haven't started seeing it yet, but the peaker type on-off stuff is going to be a big fatigue factor for big AC induction motors. Okay, and we can see how displacement amplitude is a function of frequency with this example as well. Okay, velocity. The velocity parameters analogous to kinetic energy makes it relatively independent of frequency response. So if I suggest an alarm level of velocity, it's basically based on what I choose for my piece of equipment. So if I have a horizontal pump, my value is 0.29 inches per second. So if I operate below 0.29 inches per second, I'll have infinite life. Okay, doesn't matter what frequency, it's flat across the frequency range. There's no slope to that line. If I operate above 0.3 inches per second or above 0.29, I'm going to have finite life. Eventually it's going to fail. So that's my alarm level. If I can stay lower than that, I'll have better outcomes on my machinery. Okay. The last parameter is acceleration, and it's inertial force. So it's a centrifugal force that's generated from an unbalanced shaft. There's an equation for that. We don't need to know how this works, but it's the mass offset. What radius is that offset? Times RPM divided by 1,000 squared. RPM is in there, meaning that it's changing with speed. Actually, it's changing with speed squared. But you get a curve that looks like this now. This is the displacement curve going this way. This is the acceleration curve going that way. Okay, so same sort of deal. Is 1G bad? 1G would be horrendous over here, but up here you wouldn't even feel it. So acceleration is a function of speed as well, or a function of frequency. Which brings me to this chart that kind of sums it up. This is what's called a contours of equal severity chart. Okay, we show velocity, we show relative displacement to that velocity, and we show relative acceleration to that velocity. We can choose any parameter we want, but when it all comes down to it, if I have a point that's right there that's 10 mils, I have to know what frequency it is. And if it's at 10 hertz, then I can calculate an equivalent velocity and see if I'm above or below that line. Okay. There's no curve it'd be tables worth of data to be able to do it for any amplitude level. So all you have to really remember is velocity is flat. There's no slope to it. It doesn't, it's independent of frequency. It's not it doesn't have any limitation on that. So from low frequency to high frequency, all we have to know is what that alarm limit is in the frequency domain. All right, so we're having a couple parameters, and we've been talking around this the last couple of seminars, webinars. This is about 4 days worth of data and phenomenal trend changes. Amplitudes are very simple, mean plus 3 sigma vibration, and what that means is the mean vibration plus or minus 3 standard deviations from that mean, and we can have lots of different statistical alarms on this. And it's constantly updating because you're constantly grabbing data. This was once every hour for 4 days, and I can see a change in my alarm levels, which is pretty impressive. There's another parameter down here. This is velocity for my main trend that I'm looking at. This is high frequency acceleration, and it's a filtered measurement that we'll get into shortly. This one's called peak view, but it's a high frequency energy. Okay. All you're doing is filtering out the low frequency. You're using the same time signal that you've used before. It's just filtered a different way, and you're looking for the high frequency end faults instead of the low frequency. And all that can be trended as well. Very good rolling element bearing parameter for detecting those types of problems. So along with the time waveform, which we're seeing basically the peaks from the time waveform, we can also do a frequency response for more diagnostic purposes. But the way that the node captures data, we don't need to capture the entire spectrum to make it useful. We can capture peaks in different frequency ranges. So we can specify the 1 times RPM range or the sub-synchronous or the harmonic ranges of interest, and we can pull a value off of that and trend each of those values. So the database setup is always changing, and it's got some really good capability. You just have to have some ideas on how to do the statistics. This would be what this is like. So I have a bin for my 1 times RPM, and that's, you know, basically I can do a spectrum, put a filter on 1 times RPM, and pull that value off. I can also do it for blade passing, for bearing frequencies, for gear meshing, all the different things in here. If I know the bearings themselves, what make and model number it is, I can put a very narrow band in there and look for these frequencies to appear. And it's very subtle stuff in the background noise, and it'd be very, very, very interesting to pull those out statistically, which shouldn't be too bad. We're going to look at the frequency now, how often something happens. There's a lot of sources, okay, when you think about it. I have a direct coupled center hung fan and overhung fan over here, but same deal. Sub-synchronous frequencies, the rolling element bearings can cause sub-synchronous. The isolation system, the springs that the structure's on, can bounce and cause a low frequency vibration that's sub-synchronous. Synchronous is shaft speed, turning speed of the shaft. Harmonics are from misalignment, looseness, blades and gears. Non-synchronous frequencies come out as belt frequencies, electrical resonance and rolling element bearings, and modulation comes from electrical problems, gears, and bearing problems. Okay, if we're only looking at the time waveform, we're not seeing the frequency content. We're not seeing the individual peaks in the spectrum and seeing what percentage of each peak is adding to the problem. But we can calculate it. So the way to probably do this would be on demand, or at the beginning or end of a run cycle, capture a full spectrum and, you know, store it in the database. Otherwise, you can continue on with just the amplitude levels, okay, the overall amplitudes. But as we talked the other days of this series, how do you calculate a frequency from a time waveform? You have to know encapsulate the entire period in time. So we start here, we go to a negative maximum, we go to a positive maximum, and then we go back to 0 and repeat. If we know that periodic event, frequency is 1 over the period. If it took 2 seconds, then it's 1 over 2, it's half a hertz, okay? Pretty easy calculation, real easy for the FFT processor as well. Okay. Frequency content. We're going to do this real quick. Sub-synchronous faults, or excuse me, synchronous faults are at 1 times RPM. The label on the pump, or on the motor, the nameplate data is probably going to tell us roughly what the unloaded speed of the motor is when it came out of the shop that built it. Okay. Yours is going to be a little bit different because you're hooked up to another machine, so there'll be some load on it, so it might slow it down a little bit. The best way of knowing how fast your machine is turning is to use a strobe light, use a laser tack, or go in with a high resolution spectrum and actually measure it. Right? So in this case, 1784 is my turning speed of the shaft. If I have a fault at 1 times or very close to 1 times, as in any case, this is the mundane way to do it, but my fault's at 1784, my speed's at 1784, I divide them, I get 1 times RPM, okay? So synchronous fault. Harmonic faults are multiples of turning speed, okay? So I have to know, how does this peak relate to that peak? 10,704. When I put my cursor on it, I divide by 1784, I get exactly 6. So this is 6 blades on a fan, or 6 blades in a pump, what have you. Right? So we have an exact multiple of turning speed. Sub-synchronous faults are below running speed. We have a peak here that's below turning speed. We put our cursor on it, divide it by running speed, we get 0.419 times running speed. So it's about 42% of running speed, sub-synchronous. Non-synchronous peaks are not multiples of running speed. I got a peak here at 5441. I divide it by running speed. I get 3.049 times running speed. Not 3 times, not 4 times. It's not a whole number. That's why we take it out to a couple of digits out here. There's 3 times. Here's my harmonic cursor, 1, 2, 3, 4, 5, 6, and so forth. There's my 3 times running speed. This is at 3.049. So it's non-synchronous, it's probably a bearing defect. Okay? You need a spectrum to be able to pick that out. Modulation events, I think I did a different example last time, but a modulation event is a series of peaks that are equally spaced. So there's a center frequency, which I have in green. If I go and divide that by running speed, I get 27 times. So 27 of something. Okay? This was on a motor, so it's probably 27 rotor bars in the motor, a whole number. Okay? If I do the same thing, I divide all these other peaks out, I'm getting some weird numbers. They're not 26, 25, so it's not a 1 times RPM spacing. That's how some rolling element bearings fail. They'll modulate at 1 times RPM. This is modulating at an electrical frequency. This is 120 hertz, or you multiply it by 60, it's 7,200 CPM, is telling me that there's a rotor bar pass problem in my motor. Okay, you don't really need to diagnose it to that extent. I'm just trying to get you an idea of there's a center frequency and there's a spacing on the sidebands, and the spacing's telling you the source, okay, and how it's modulating. So that's one type of modulation fault. The last little tidbit for our analysis here of time, amplitude, frequency, and phase is motion and direction. It's telling us how that piece of machinery is moving. That's going to be one of the 6 or 7 phase tests that we perform, and it's going to narrow down the response, and we'll be able to pick out the root cause. On the table, these are the phase diagnostic icons. This is the group. So it's mostly synchronous problems, right, in one natural frequency. This gear problem doesn't play into it. So there's 3, 5, 10. There's 10 different phase type problems here that we'll have to dig into. They all have the same spectrum. They all have a dominant 1 times RPM, possibly a 2 times RPM harmonic, and they look enough alike that we can't tell one from the other. Okay, so if we don't do phase analysis, we're not going to be able to define any of those problems. Visually, gives you a better idea. This is offset angular misalignment. I have my analysis I've done across the coupling in the axial direction, and they're 180 degrees out of phase. I do that same thing in the vertical direction, and they're 180 degrees out of phase. This is an offset misalignment, either horizontal or vertical, depending on the direction. Okay. Phase, it's how the system is vibrating, defined as the relative motion to a fixed reference, like a laser, a relative motion to a rotating reference, measured in angular degrees. The meaningful phase numbers are 0 degrees, 90 degrees, and 180. It's the forces in the machine that are making it correct and push back and forth. Okay, so if we can figure out phase-wise how the machine's moving, we're going to be able to decipher the problem. How's it done? Real rough idea of how it's done. We rove the transducer. We have a piece of reflective tape on the shaft somewhere that's giving me a position reference. that tach is hooked up, and I look at the transducer output and the tach output on the same scale, and I can see that one rotation, every time it rotates into view of that reflective tape, I get a pulse. Every time the heavy spot goes by, I get a pulse. So if I know the distance between that tach and that pulsing, and I can equate it to phase, I can see what angle my heavy spot is. Okay. But even better, that's more for balancing. Even better for a phase diagnostic, my tach is at a single position and doesn't move. Everything's relative. Every phase measurement I make is relative to that tach location. So I can make little tick marks of, I leave the tach where it is, I put my transducer in a different spot, and this waveform is going to shift around. So it'll tell me a different phase number for each location. You really have to do it live. And in the vibration, introduction to vibration class, we have a motor demonstrator. We go and we do a phase analysis, and we mark the bubble charts. So, I know that a lot of you out there might not get this or really even care, but it's a great technology for deciphering problems. And if we don't do it, we're kind of lost. These are the phase rules. So there's 6 different rules. We're looking for unbalance, eccentricity. We're looking for overhung rotor unbalance. We're looking for bent shaft, misalignment across the coupling, cocked bearings, and soft foot conditions, or mechanical looseness type A. Okay, we're looking for all of these. Anything with a phase icon in it, that's what we'll be able to distinguish. Okay, last thing, we're going to look at bearing defect frequencies in the velocity spectrum. We're going to look at ultrasonic impact and friction, and then the 5 failure stages for rolling element bearings. So this is the high frequency technology that we haven't really talked about yet. Okay, so far we've been focusing on just velocity measurements, overall velocity for trending purposes. This is another trending program that we can look at. Within the same accelerometer, doesn't require any new technology, same time waveform coming out as we use for the lower frequency stuff, we're just filtering it differently. So it's all software. Should be transparent to you, the user. Okay, cage or fundamental train frequency always occurs sub-synchronous. I have statistics here from 18,000 rolling element bearings. The average cage frequency is 0.428. It ranges from 0.4 times running speed to 0.46. So there's a little bell curve under there, and this is where it shows up. So my synchronous or 1 times frequencies here, it's below running speed. A little less than half of running speed is typically where it shows up. My example at 749, I divide it by running speed, I get 0.42, so I'm within that range, right? Oops, where am I? 0.4, yeah, 0.4 to 0.46. So chances are that's a cage frequency that's showing up in my spectrum. Ball spin frequency, its average is 3.88 times running speed, and the range is 1.9 to 5.9 times running speed. So it's a lower frequency range here. My example, I see a peak and it's at 0.5441 times running speed, or excuse me, CPM. I divide it by turning speed of the shaft, I get 3.049. Not 3 times, it's non-synchronous, 3.049. Okay, so very likely a bearing defect. My next example is ball pass frequency outer. It's a fault on the outer race, and the balls are exciting it every time they hit it. Its average is 7.757 times running speed. The range is 4.2 to 11.3. So this one's out here at 14,619. Not sure what it is. I put my cursor on it, get that number. I divide it by running speed, and I get 8.194. It's non-synchronous. Chances are it's well, it can either be an outer race or an inner race. Uh-oh. Sorry, folks. For some reason, there we go. I think I took care of it. My computer got unplugged. Excuse me, technical difficulties. So 8.149, it could be either an outer race or an inner race. Okay, we're not sure, but it's in the range of both. The last couple here, I have a peak at 17,563. So you know the drill, you divide it by running speed, 9.845. I got another peak, 35,127. I don't know what the source of this is. I divide by running speed, and it's 19.69. It's also non-synchronous, but it's exactly twice the first one. So this is the fundamental bearing defect. This is the harmonic of that. So the exact multiple of that. Okay. What is it as far as the range? It is either an outer race or an inner race. We don't know for sure. Okay. Here we have something unusual happening. This is some modulation. Okay. I have a center frequency and I have equally spaced sidebands. Okay. So I try to find the center, 20,516, and I divide it by running speed. I get 11.5. Do the same thing for each of these other peaks, and I get 10.5, 9.5. So they're separated by 1 times RPM. This is typical of an inner race bearing defect. It's a non-synchronous frequency. It's in the right range, and it modulates 1 times RPM because it's going in and out of the load zone every revolution. So if this bearing is vertical, down in the lower part of the bearing, it gets more load than when it does at the top, and that pattern repeats every revolution. You'll get a modulation at 1 times RPM, and it shows up as sidebands spaced at 1 times RPM. Okay, so there's bearing defects. We know how to identify them. If we don't know what the bearings are, we know how they present themselves. They're always non-synchronous. They always should be in a certain range. If we want to know if it's coming from the inner race or the outer race or the ball or the cage, we can kind of figure it out. But there's a better training method that we'll see before we'll ever see anything in the velocity spectrum. This is ultrasonic demodulation. Okay, so we're going to look at that. We're going to look at that, and then we're going to look at the failure stages of bearings. This is something called, the whole thing is called demodulation. So what it's doing is it's filtering the time waveform that we would normally collect, and we're looking for high frequency impacting. Okay, and we'll walk through the 7 or 8 steps real quick and see what's going on. I've got about 8 minutes left. We pull the same time waveform, goes into our analysis tool, and we do a little software magic to filter it and change it. So the raw signal has all the residual imbalance, looseness, misalignment, electrical, hydraulic, bearing defects, gear meshing. It has everything in it. Okay, we don't care about the big wiggles. We're looking for the real high frequency stuff that's riding on top of it. Okay, so we have to put it through a filter. Typically, it's a high pass filter or a band pass filter. I believe the new Grace transducers have the capability of making one of the transducers a high frequency, or much higher frequency. It goes from 1,000 hertz up to, I think, 8,000 hertz. So we'll be able to capture much higher frequency events. So if we put this through a high pass or band pass filter, we eliminate the low frequency wiggles in it, and we only get the high frequency stuff riding on top. Okay. If we zoom in on that, we'll see a couple of things. We'll see a pulsing event. So every time a ball hits that fault in the raceway, bing, and it rings down, bing, bing, bing. So there's a certain rate. The impact rate is very important. We could also really zoom in and see what the ring down pattern is. So we could see that it's a natural frequency, typically, that you're ringing, the housing structure or something. But we don't really care about the ringing part. We care about how often did we ring the bell. That's telling us what the hammer is. The hammer is the ball hitting that fault in the raceway, and then hitting it, the next ball hitting it, and the next ball, and the next ball. It will be a prescribed rate. We'll be able to decipher what the source is. Okay. We get these transients, or this string of transients, and it's very low amplitude, and they're all spaced out in time, so we have to zoom in on them. We can put it through some type of software peak detection. something called rectification, where we can eliminate or multiply it so it looks like a bigger peak. And there's another thing called time constant enveloping, which is the blue line right here. So we're drawing an outline of the pulsing event. What we really care about is that peak event. Okay, so each vendor has proprietary signal processing to do just this. And this would be something that Grace would develop in the coming months. We'll put it through a low pass filter now. The low pass filter eliminates the high frequency events in there. And like I just mentioned, we don't care about the ringing. We care about how often we rung the bell. The curve, the blue curve down below, is the outline of that pulse rate. And it's called a sawtooth profile. This we can trend. So we put it through our peak detector and we can trend the level that's coming out of this. And I made it look pretty variable, but pretty clean, but it can be jagged and different. So we'll trend this over time. And when it goes into alarm, there's two possible things it could be. It could be either impacting due to a defect in the raceway, or it could be friction from lack of lubrication. So either way, we probably give it a shot of grease and see if it settles down. And that works quite a bit, but there is, if it comes back, there is some type of damage starting in the raceway. Very early indication. This isn't where you change the bearing. This is where you maybe step up the trending a little bit. These are the two things that you'd see in the spectrum. So you can do a spectrum of that sawtooth waveform. And if there's no sawtooth peak in there, there's just noise floor, random noise, you'll see something like that. So every survey, this will go up and down a little bit. We can trend the overall level of that energy. If it is a discrete peak due to a piece of raceway coming out, little chunk of metal being separated, you'll see a discrete peak show up, a discrete impact in a whole string of harmonics. So you should be able to identify the source. This should be non-synchronous, and it should equate to an inner race or outer race defect frequency. And last, the 5 failure stages of bearing. I've got 2 minutes left. New bearing, you're going to have, it's stage 0. A lot of people don't even know this exists. It's a new bearing break-in period. You have machining marks on your raceway that you're trying to get rid of. If you do a spectrum, a velocity spectrum, a normal spectrum, you won't see any bearing defects. If you do an ultrasonic spectrum, you'll see just random noise floor. All you're doing is breaking off the little peaks, the little errors in machining, and smoothing out the raceway, actually. Stage 1, early micro level subsurface faults or lubrication issues. You're going to get no response in the velocity spectrum, and you're just going to get random noise floor. So we're just starting to wear the bearing, and very subtle. You probably won't even see it. Stage 2, you ongoing micro level subsurface faults or lubrication issues. Lubrication issues with just random noise, we can address that with a little grease. Subsurface faults, that just means that we won't be able to see them on the raceway. They'll be below the raceway. There'll be cracks in the metal lattice structure. 3, macro level, visible surface damage. Evidence appears in the ultrasonic spectrum and the velocity spectrum. So stage 3 is where we start seeing defects in the velocity spectrum, defects in the ultrasonic spectrum. This was a fracture below the raceway surface, and it pits out when it loses all the contact there. So they're deep edges is what you're looking for. This is a serious defect, so the bearing's got a finite lifetime left. Stage 4, pronounced visual damage, visual spectrum defect, harmonics, and sideband modulation. It just goes to pot. So this was a bearing in a nuclear vertical pump in a nuclear plant. And they asked me to take a look at it. It had all kinds of bearing frequencies, non-synchronous peaks in the velocity spectrum, Notice they're not very big, but there's a lot of them. And in the demodulated spectrum, the ultrasonic spectrum, there's peaks and sidebands on the peaks, which is unusual. So they were degrading extremely fast. And when they pulled it out, there's debris all over the inside of the bearing casing. Pretty bad fault, very close to failure. All right, I think that's it for this time. I appreciate everybody coming out for these webinars. It's great information. If you're interested in training, I do a lot of that, and I can do it live, or I can do it through webinars, or I can do it online at your own pace. Doesn't matter to me. If you guys have questions, I'd love to answer them if I can. Do we got anything, Nick?
Yeah, we got a few today. Is there a good simple formula to convert acceleration G's to velocity inches per second?
Yes, there's a, I don't have it handy, but I was just playing with it before this started. I can send it to you. If you want to, I think there's an email address attached to the question, so I can send it to you. If Nick, you can single that out. Yeah, you can change between velocity, you can change between acceleration, and you can change between displacement.
Okay. For existing equipment, what do you recommend in regards to installing sensors with minimal downtime and relying more on mathematical modeling? In other words, do more calculations with less sensors?
Ideally, you want, less sensors means the one sensor is going to have to distinguish between two different bearings that are maybe 3 feet apart. You're not going to be able to do a good job that way. It would be great to have less sensors. They do, I think you make, I might be talking out of place, but I think you can get a node that's a single axis node that might be cheaper, and do a triaxial on some and do a single axis on another. I'd have to look into that. I'm not fully versed on all the different product lines from Grace yet. But if you,
right,
that's the biggest problem, is being able to cover multiple bearings with, less transducers. You'll miss something.
On that previous formula question, the chat blew up. Everyone wants to get their hands on that. So if you want to send that to me after this, I can shoot that out to everyone in the follow-up email.
Yeah, I can do that.
All right. Okay, there's one. Can you help me define the instrument range calibration?
Define the instrument calibration. Are you talking about the millivolts per G? If that's the case, it comes on the literature from the transducer, and it'll be, close to 100 millivolts per G, but it might be 98.4, and you put that in, and that's the exact calibration factor for the transducer.
Yeah, that's what he was asking. Okay.
Yeah. Okay.
Let's see. Getting a few more comments in here. How often are these online sensors needed for calibration?
It depends on if you're in the calibration business, then they need it all the time, but probably not very often, probably maybe once every year or two. And you can do that by just, if you have a portable shaker, you can buy them from, I don't know, IMI, PCB are two different companies, and then CTC technology. Anyway, they're small shaker units, and you can attach your accelerometer to it, and you put a 1G 100 hertz signal into it, and it'll tell you how far off you are from that. So it basically starts at 100 millivolts, and the drift in that will tell you where you are. So you might be, it used to be 98.4, now it's 96.2. and it really doesn't calibrate, it doesn't change it, it just tells you where you are now. There's always over time, there's a little drift in the calibration factors, but not much.
All right. I see a few comments in here requesting specifics from this presentation. We'll be sending out this PDF in its entirety after the conclusion of the webinar, and this follow-up email we'll send out. We'll try to get that out by the end of today. A follow-up question to that previous one, Dan. Is there any ISO standard for calibration?
I'm sure there is. I can't think of what it would be right now, where you'd find it. Andy might know that, Nick. One of the guys at Grace probably knows all the calibration information. He might be.
Yeah, guys, please feel free to reach out to us. So I apologize, our sales email address is not listed here. If you have specific questions for Dan's presentation, you may email him there. I'll provide an email address link in our email going out where you'll be able to reach out to us regarding our products. Last question, will all 3 parts be available for offline viewing? Yes, we're gonna upload this to YouTube, and then we're gonna do some editing, and we're gonna combine all these into one entire video, all 3 sessions, and we'll distribute that to you guys as well. That one will be coming later, but today's session will be up today, and we'll send that out in the follow-up email. So thank you guys all for your questions. Again, anything related to the presentation, feel free to reach out to Dan. Product-wise, reach out to us here at Grace. Thanks again for coming to this 3-part series. We had, almost everybody, it seems, came back to visit each and every one of these. So we're very happy. You guys really got a lot out of this content. Thank you very much, Dan. Did you have any other closing remarks?
No, thank you very much, everybody that stuck with me and listened. If you have any constructive or, if you hated my presentation, tell me that too, but constructive criticism is always welcome. I thrive on making the stuff better every time.
All right. Awesome. Well, thank you, everybody. That concludes the webinar today in the series. Take care. Thanks, Dan.
Thanks.